Excellent. Okay, so in the last class, we were talking about section 3-1, and that was all about the mean, the median, and the mode. And when we're thinking about each one, they all had something to do with what we called measures of central tendency. And measures of central tendency refer to what value or what values do the numbers in data set tend to gravitate towards. And when we started getting into section 3-1, especially with the mean, we started finding out all kinds of little symbols, shorthand symbols that we're going to need to know later on for formulas. And I'm going to go up here to the first name I have is Stephanie, Odessa, starting off with the A's. So Stephanie, when we're thinking about the mean, what I just stopped to get somebody into the video session here. When we're thinking about the mean, what two symbols do we have that we can use to record the mean? Like we have one for population, we have one for average. Which is which? Or if you just want to throw us out one. And Stephanie, you might need to turn on your audio. Okay, I'll come back to Stephanie a little bit later. The next person is, looks like it says Talia Andrade. Talia, can you hear us?
Yes.
All right, Talia. So we're talking about the mean, and we have these two different symbols for the mean. One for population and one for average. Which is which?
I don't remember.
It's okay to look in your notes, guys, if you need to. Anybody can help out Talia. Or is it Talia?
Talia, you got it right.
Okay, good, good, good. I have to think of the singer. I don't remember.
Would it be the X bar?
Exactly. Yes, it is. X bar comes from the sample average. And what's the one we call it that comes from the population average?
The upside down X.
Mu.
It's like a UP. Yeah.
Good, good, good. Well done. It's called the mu, like mu, but with a U, mu. It's a U with a tail hanging off of it. And why do we have two different symbols? Like, what's the point of tracking the information, whether it came from a sample average or a population average? Like, why would it be a cause of concern down the road? And I'm going to stay with Talia on this one.
Because a population average, I don't want to say it's more accurate, but it gives a bigger sample size than the sample itself.
Okay, your first word, your gut reaction was spot on. When you said accuracy, you're exactly correct. Our information that we're going to take from the population would be considered more accurate because we have data that we're using on every single person. If we're looking at a sample average, a sample doesn't have everybody in it that the population does, so it would be considered less reliable and even riskier. So that's why we're putting the tags X bar for a sample average and mu for the population average, because down the road, we have to know what source the information came from. It's going to help us out with understanding how risky that number is that we're about to plug into a formula. And I'm going to go to Natalie I think this is Brangaccio. Is that how I say it, Natalie?
It's Brangaccio.
Oh, I was way off. Brangaccio. All right. So Natalie, when you think about the mode, what comes to your mind? Like if you're going to say to somebody in two sentences what the mode does, what would you say?
The most common number.
Very nice. Excellent. Most common number. Now, do you think the mode is always going to be a member of the data set?
Yes.
It might be. If we find that the mode is, let's say 3 is the most occurring number in the data set, then it would be. And remember, you can have a data set that's bimodal. It has 2 modes. Trimodal, it has 3 numbers that are the most commonly occurring, but the data set can also have no mode, which just means no number is repeated more than once. So it might be a member of the data set, but there might be no mode at all. I'm going to go down to Zachary de Gregorio. So Zachary, when we're thinking about the mode, we know it's the most common number in the data set. when would be a real advantage that it has when the mean couldn't be used at all? Like, what's a really strong advantage of the mode?
It's easy to find in the set.
Okay, it is very easy to find. That's true. It doesn't require you to do computation. That's a smart comment. Are there other situations where you can use the mode where you couldn't use the mean?
I'm not really sure.
Okay, what do we think, guys?
Would it be because it works with qualitative data as well?
Bullseye, that's exactly right. It's going to work if you have a data set that's non-numerical. Like if you're recording information on, we worked an example, passengers in a plane, male, 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 female, we can get the modal gender. And let's talk about let's see, the median was the one we didn't mention yet. I'm going to go to Ms. Hernandez. That's Amanda. And Amanda, when we're thinking about the median, what's the median doing?
It's finding the middle number.
It's exactly correct. It's exactly what it's doing. It's going to find the middle number in the data set. Now, what do you have to remember? If your data set's even or odd, what could potentially happen to you?
I don't remember.
Okay, what do we think, everyone? Like if your data set is right? If your data set is odd or even numbered, what would be the implication about how you actually go and take the median under those circumstances?
You divide the numbers by 2, the 2 medians.
Yeah, right. If we're even number of values in a data set, then we're going to have to average the middle 2 numbers. And that's usually one of the most common things missed on a test. It's not a lot of points to lose, but we just kind of sometimes forget to go and count up the numbers of the data set. Okay, so we talked about mean, the median, and the mode. When to use the mode instead of the mean.
Professor, so in that instance, we divide the 2 medians?
Exactly correct. You're going to take the 2 innermost numbers and you'll divide them by 2 and you'll be done. Amanda, are you actually out on a call right now? It looks like you're inside an ambulance.
No, I'm coming back from one.
All right, good enough. Thank you for saving lives today. So if we're talking about the median, when would the median be really useful? In like what situation where you would want to go with the median, but you would not want to use the mean? You would want to stay away from it.
If the numbers are very high or very low.
Nice, very nice. Okay, so Deanna's right on. She's saying that if we have an extreme high number, extreme low number, it's going to mess up your mean a lot, but your median would still be preserved. So you want to use the median to represent your data set. So what I want to make sure you guys remember really well is we know how to find the median, mode, and the mean. Make sure you know the advantages of when to use one and not the other, because that's probably going to be like 6 questions on the test. And we talked about them. In case you forget what we talked about, we also have inside the PDF, there's one page that has a bright red circle around it. It has a chart and it's summarizing all the different measures of central tendency, the mean, median, and mode, and when to use them, which one versus when not to use another. And the information is laid out really well. Make sure that you can pretty much recite that page without looking at anything and understand the rationale behind their comments. And you're going to be really happy when you get to that section of the test. We're going to start to talk about section 3-2. Anybody have any questions about anything from the last class before we kick off here? And I don't see anything coming in under the chat window. So I'm going to go ahead. I'm going to flip our screen over to the presentation screen. And can everybody see this huge bright red square?
Yeah.
All right, great. That's not our presentation yet, but I find it's a really fast way to share the screen because they only give you the screen that's showing on whatever software page. And I have all these different windows open, and one of them is a huge red color. And I know exactly where to go to turn on the screen share to get the software we need. Okay, so measures of variation. When we're in measures of variation, the formulas get pretty complex here. So what we're going to do before we get into math, before we get into formulas, calculations, we're going to have a chance to talk about conceptually what the variation section is all about. Like what it's there to help us understand the benefit of analyzing it. And then once we have that down really well, like once we know everything about it except how to calculate it, then we're going to go and we'll start to calculate it. Okay. Now where we'll start is I'm going to put two data sets up here, and I'm going to go nice and slow over this part because I know people are trying to write things down. A data set on the top and a data set on the bottom. And what we're thinking about is if I was going to give you guys $1 million, you have to pick one data set and you're going to bet on which number comes next. So the question marks that we see at the end, they stand for the next number in the sequence on the top and on the bottom. And just have to get that number right. I mean, I don't have $1 million to do this. I wish I did, but I don't. To get that $1 million, you just have to pick and get the number right that comes next. So about ready to bet on it. Which data set do you think you would like? And looks like we're up to Moshe here. Moshe, would you go with the data set on the top or the bottom? That's Moshe Kraus.
I would go with the top one.
Okay. Most of us would go with the top one. Why do you like the top one? Moshe, what's special about it?
It looks less complicated.
Easy.
Yeah.
Okay, Tada. I got it the other way around, didn't I? I said you're welcome. Okay, Moshe's right. We probably want to use the top one because what's our guess that the number that comes next is going to be, Moshe? Or anyone that wants to jump in there, what number is almost for sure coming next in that data set on top?
Number
One.
Excellent. Well done. Beautiful. We know that because the data set looks very, very, very predictable to us. It's not changing much. So when we're thinking about the data set on the top, from one number to the next, it appears to vary just a little bit. So we would describe it by saying that data set has a really low variance. And some things that are synonymous, what's in a low variance, that data set appears very stable because we've already commented that it's not changing much. It's pretty much stuck between, what's the highest it goes up? About 3, doesn't go below 1, so very, very stable. It's also predictable because Moshe was able to guess the next number real fast. That's a big advantage for us in statistics because if we want to forecast something later on, we're going to base that forecast on historical information. And if the historical information is very stable, it's going to make it much easier for us to do our prediction. That also means it's going to be more risk-free because we're more likely to get the prediction correct. Everybody okay so far with the idea of what would be describing a data set that has low variance? Okay, so what about the data set on the bottom? The data set on the bottom is going up and down in leaps and bounds, so we're staying away from that for betting. It doesn't appear to have a low variance. In fact, it has a really high variance. And we probably, would we describe that as being stable or not? What do we think?
Not.
Not at all, right. So we're going to say that's unstable. And what do we think? Predictable or not predictable?
Not.
Not at all predictable. So if we're going to do some kind of a forecast and we're basing it on a data set that has a really high variance, gee woo, that's Ms. Lee, gee woo Lee. Do you think that's going to make our job really easy to do or really hard to do if we're basing a forecast on a data set that's very unpredictable?
Hard.
You are correct. So it's going to be more risky, a lot harder to get the number right. So anybody have any questions on difference between high variance and low variance in terms of the properties it's going to give a data set? Okay. Now make sure that you feel really good about that. On the test, I'm probably going to ask you quite a bit of questions. Like a high variance we could be describing as A, unstable, B, unpredictable, B, risky, C, easier to forecast from. And I'm going to ask you which one doesn't fit. I'll probably do that for high variance and low variance with a few different questions. And we're looking right now at the tidbits that'll help us understand our way through that. Okay, I'm gonna skip that slide. So now we're seeing this stuff about how much a data set can vary. It can be really important for trying to factor in risk when it comes to a data set, because it'll tell us how much error we need to involve in our calculations. And companies spend a lot of money trying to do that. Anybody ever heard of a risk department in a company? Like what do risk departments do? Like if you're working for a credit card company and you have a risk department and somebody is applying for a loan, what do you think the risk department is going to do? What are they going to assess that person for?
Any risks in their investment they'll be making in you?
Sure, yeah, they're going to look and see, you know, how predictable is this person, because they want their money back when they lend them a loan. So when we start to think about how we could end up quantifying risk or variability as we're looking at it, how would you do that? And we have three different ways: the range, the variance, and the standard deviation. We're going to learn how to calculate all three, and then we're going to learn, well, why do we need all three? How come just one isn't enough? So we'll eventually find out that the range we've seen before, we'll talk about it again. We're going to find out it's really quick and fast to do, but it has a pretty big problem, almost like a shortcoming that we're going to find really stops us from getting very sophisticated with the data set. And we're going to find out pretty fast that there's something we need that's a lot more advanced than the range. That's going to bring us straight to the variance. So the variance is tougher to calculate. It's going to give you a lot more intel on the data set though. And standard deviation is kind of joined at the hip to the variance. So we'll find out why somebody would use a standard deviation instead of a variance, under what situation they would want to refer to one and not the other. Questions on anything so far? Okay, so what we're going to do is we're going to start to think about getting the range underway. And we'll do a real simple graphical idea of something we need to see as an introduction to the range first. If we're going to paint a room in a house, we're going to go out and use paints. We need to paint the room, and we want the kind of paint that dries as quick as we can. I mean, as quick as it will. We go to the Home Depot, we find somebody, and somebody that works there, we say, give us your brand of paint that dries the most quickly. And that person gives us two different samples of drying time. They say, here's drying times for brand A, here's drying times for brand B, and use the information to figure out what you want to buy. So when we look at each data set, just so we know what we're looking at, data set A says brand A. These numbers up here are in hours. So what it means, if we're on the leftmost value, somebody painted a room and it dried in 10 hours. The next bucket says 20. So somebody else painted a room and the room dried in 20 hours. It looks like in another instance, it took 50 hours to dry. In another instance, as many as 60. And data set B has the same type of a setup. We have all the different dry times for that particular paint. And next person on my list I have is Ms. Munn with an M. I think that's Aram. So Aram, if you were going to buy one of the brands of paint, you're going to paint a room, which one do you think you would want to use? The data set A or brand B, based on the information you're seeing in the graphs here? I don't think Aram is got the audio on yet, so I'm going to go to William O. We're at the O's. William, what are we thinking when we look at data set A compared to data set B? Like, if you were going to buy one of the brands, which one would you probably lean towards purchasing when you're thinking about how fast it's going to dry?
I would say the top one.
Okay, so you're going with the one that drives between 10 and 60 hours. Now, do you think data set B would have any advantages over data set A when we're looking at the drying times? Like when we look at B, anybody notice anything about B that might give it a little bit of an advantage over A?
It doesn't go to 60.
Okay, it sure doesn't go to 60. What's it trapped between?
35.
Not 35.
25 and 45.
25 and 45.
25 and 45. Yeah.
Beautiful. Well done. Okay, so it's between 25 and 45. Brand A is in between 10 and 60. Which one do you think is going to be more reliable?
Brand B.
Yeah, because brand B has something that begins with the letter P that we could use to describe it. What does it make it more of that begins with a P that brand A doesn't seem to have?
Precise.
Okay, maybe precise.
Predictable.
Yeah, right. Both of those words together. More precise and more predictable. So it looks like brand B might be a little bit more reliable than brand A is. And we're noticing the numbers are spread out so far along the data set, they're very widely dispersed. Brand B, the values are more closely situated around the mean of the data set, aren't they? So let's talk about how we could quantify what we're seeing. Well, we've noticed a couple characteristics. We like B, it's more reliable. And we can quantify what we're noticing with the range. So what the range is going to do, it's going to measure the physical distance across the data set. In chapter 2, when we use the range, it's going to take the maximum and it's going to subtract from it the minimum of the data set. Now, what it's going to figure out is the data set that has the highest range must have more distance that it's taking up across the number line. So that would tell us what data set is more widely dispersed. Now, what I want you guys to do is take a second, take a few seconds. I want you to calculate the range of A, the range of B, and as soon as you get it, just go ahead and throw it in the chat window there. Or if you want to shout it out, you can do that too.
Brand A is 50.
Okay, brand A is 50.
Brand B is 20.
Right, and I have everybody's photographs here and this text message, and it just kind of dumped itself over the screen. I reposition those. Okay, so it looks like it's definitely the case that data set A is taking up much more room on the number set than B is. Everybody okay so far with comparing the ranges? Questions on anything? Okay, swell. So we're kind of getting that the range of data set B is smaller. And we found that out really quickly. The range took us just a minute to calculate. So it's quick and it's fast, but it's got a lot of problems too. And one in particular that we're going to look at. And this problem basically says, okay, the range is nice, but we can't use it because it's not going to give you all the information that you need to see about a data set. And to see why that's going to happen, we're going to use kind of a graphical example. So we're not going to use formulas yet, no calculations, don't worry. If we work with brand A for a minute, and imagine that we just had a shifting in the data set values. We'll keep the original numbers there just for comparison purposes, and we're going to put the new values in X's up here on the top. So as we're looking at that, Sharon, did we just have a really big change in the consistency of the data set? And it's, oh, I'm sorry, I said it wrong, Shannon Osborne.
Yes.
Okay, where did all the values go, Shannon?
To the left.
Exactly correct. They all went to the left. So would it be fair to say, Shannon, that the data set is more crunched up now?
Yes, because there's a lot more data on the left.
Sure, there's a lot more data on the left. Does it look like it changed the variability in that case?
If we're gonna look at the X's, yeah, because they're all in one area. Mm-hmm. But if we're looking at the one on the bottom, no.
Exactly correct. Yeah. So the X's, just like Shannon was saying, change the variability. They're all crunched up together. Now, what's the range going to be? is the range different? And I think I put the next line up too fast. What's the range if we calculate it out of the new data set? Will it be the same, do you think, or will it be different? I'm going to bring this one to Stephanie Pignotti with a P. Stephanie, is it
Yes.
going to change or stay the same, do you think?
If it would change.
What do we think, everybody? Would it change or different?
I think it would stay the
Be the
same.
same.
Stay the same.
Yeah, okay. Now, why is it staying the same?
Because there's an X still on 60.
Yeah, there's an X on 60 and there's an X on 10. So what's happened is the range will hold to the same value. That's because the highest number and the lowest number, Stephanie, they're staying in exactly the same spot. So what that means is all these numbers in the middle here, we're down to Lauren Reeves with an R. Lauren, all those numbers, can the range see all those numbers when it's doing the calculation? The numbers are circled in green there. Can it detect them? What do you think?
It cannot.
You are correct. It can't. Now, is that really good or is that really bad, Lauren?
Well, for the sake of this example, it doesn't really work because it doesn't show that the data is more concentrated to the left.
You are right on the bullseye. It's not going to notice any of that. So that gets us a little upset and kind of worried because it means the range can't see anything in the guts of the data set. All it can see is the highest number and the lowest number. So for analytical purposes, that's really bad because it means the range is not going to be sensitive at all to anything in between the highest value and the lowest value. And definitely remember this. This is going to be on the test. You're going to need to know that the range is the least sensitive measure of dispersion because that's why we need the variance eventually. Everybody okay so far? Any questions anybody has? Okay, I'm just going to give another second or two, okay? I see people still trying to write stuff down.
Thank you.
Mm-hmm. And I'm just going to take a second and give the chat room a double check to make sure there's no questions coming.
You said that the range will always be the least sensitive.
Yeah, it's always going to be the least sensitive. And the reason why it happens is because it can't see any of those numbers in the green box. It can't see the guts of the data set. So what's happening is it can't detect any of the values that we have circled in green. It's blind to what's happening there. Make sense?
Yes, because it only focuses on the max and the minimum, correct?
That's exactly right. Yeah, only can see the maximum and the minimum. And we would love to stay with the range forever because it's easy to do, just subtract. That's where it gets us into trouble. We would say, well, it might be important if even one number changed in the data set. Like that, it could be, imagine you're tracking asteroids and one of them just slipped in the orbit and it's a little 20-mile long asteroid headed towards Earth. We would need to know about that. Okay, so what's going to happen is this is going to motivate our need for the variance because we have to have some kind of a measure of this dispersion stuff that'll take into account the position of every number in the data set. So what the variance is going to do, it's going to consider all those positions and it's going to try to measure the average distance between each value and the mean. So again, it's going to try to measure the average distance between each value and the mean. What we'll do is, before we calculate the variance, we're going to talk about what both of these statements mean, because I want you to have a really good idea of what the calculation does that we're going to end up doing. Questions on anything yet? Okay. Anybody need another minute writing things down?
Yes, please.
Yes, please.
Okay, I'm going to give you guys a second to catch up, and I'm just going to double check the any questions in the chat room.
Professor, you want us to write that down? Is that going to be on the test?
That's a great question. And it's not going to be on the test. What you'll need to know is eventually the variance is going to measure the average squared distance between each number and the mean. And that was a really great question. The reason why there's a little bit of a discrepancy is because we're going to find that right now we're trying to get the average distance between each value and the mean. So we're going to calculate something to make that happen. And we're going to almost get like 95% of the way there. And then we're going to need to do this fudge factor to fix something that's going to go wrong. And that fudge factor brings us to the standard deviation. The standard deviation is going to eventually measure what you're seeing right on the screen. The variance is going to measure what you're seeing, except the distance is going to be squared. Anybody still writing stuff down? Okay, so what we're going to do is just make sure we have the concept down here. So what's going to happen is if we have a data set that has a very low variance, do you think the values would be really crunched up around the mean of the data set or really scattered apart? Where do you think they would be? And I'm going to bring this to, my next name is Kayla Racchetti with an R. So Kayla, what do you think?
I'm sorry, could you repeat the question?
Yeah, so if the variance is going to try to measure the average distance, each number is from the mean, and if the variance is really low, do you think the numbers in the data set would be hugging the mean, really close to it, or they'd be scattered very far apart from it?
If they're really low?
Yeah, if the variance is really low, numbers are going to be really closely hugging the mean or very far scattered from the mean.
Close?
You're exactly right, yeah. So I like to think of the photograph of the people in the elevator. See how everybody's all kind of crunched up on top of each other? They're very, very, very close together. So I like to think about that picture when I think of a low variance, because it reminds me that the numbers are all crunched up on top of each other right around the mean. And I guess if this was a picture from today, all those great people would have masks on and everything and all that stuff. The picture on the right is a little more like it, isn't it? So the picture on the right, higher variance, each number is a much further distance from the mean. So what are those people doing? Are they all crunched up around each other, or where did they go?
Spread apart.
Yeah, they're
6 feet apart.
Yeah, they're 6 feet apart. They're doing the social distancing. So that's what I think about when I see a high variance. I know just like those people that are like that far apart from each other, the numbers are going to be really far away. Everybody feel really good before we start to calculate out the variance. Any questions? Okay, so we're going to actually start the variance calculation then. And what we'll do is we're going to use that same data set that we've been working on for a while to calculate. And I put that phrase up at the top so we have something to work off. We got to find a way to measure the average distance each number is from the mean. So the first thing that we're going to do is we're going to make a great column here. We're going to list all these numbers, the same numbers in the data set we had before. We're just going to drop those all right down there. And we're going to start to make a bunch of columns in here. Now I know that I have to take each of these numbers and figure out what the distance is from the mean and then average that number. So to help out, we're going to make another column for average, and we're going to fill in the average going all the way down. Now, you don't have to write it on every line, but I like to do that because I have to do subtraction next. And when we do subtraction, it just makes it a little easier. So I've got the column for X's, a column for X bars, and Isabel Rodriguez is my next name. Isabel, what do you think we're going to do with those two columns?
Hold on. Ask me again, Professor, I'm sorry.
Sure. We know that we need the distance between each value and the mean. So what do you think we're going to do with those two columns? Here's a hint, say subtract.
Oh, I guess we're going to get the range, subtract?
Yeah, you're going to subtract. You don't have to worry about the range anymore. We're kind of done with the range for a while. But we're going to subtract. And when we take each value, I'll give you guys a minute to get this copy down. When we subtract each value, we're going to go ahead and write them in the next column, just like so. And I see people are still copying down, so I'm going to hold on a minute here. And they're going to. I see a lot of people still writing out, so I'm going to be really patient and make sure that everybody gets what they need to. Oops, sorry about that. That's my fault. I'm going to put that back right now.
Yeah.
Anybody need another minute or two?
Yes, please.
Okay. This is just not one of those concepts we want to speed through. Now, as we're kind of writing these down, one thing that we're going to start to think about is everybody agree that we got the distances between each numbers and the average right now. Would that be fair to say?
Yeah.
Okay. Now, I know that variance wants the average of all those distances, so it probably makes sense that I would want to get the average of all of these numbers right here. There's going to be a little problem, though. When we go to average these up, what's going to go wrong for us? What's going to go very, very wrong for us? And I have Ashley Sanford on my list next. Ashley, what's going to happen if we try to get the average of all these?
There's negative numbers in there.
Yeah, like there's a negative 25 and there's a positive 25. There's a negative 15 and a positive 15. There's a negative 5 and a positive 5. And we know the average would first require us to add all those numbers up. So if we add them all up, Ashley, what's going to go very wrong?
They're going to be 0.
Bingo. Yeah, everything's going to be 0. And then are we in a jam? Can we do this?
No.
Say, no, our hands are tied. We can't really do anything with this. So we need that average, but, oops, sorry, I hit the button too soon. We need the average. We're not going to get anywhere. So what we have to do is we have to find some way to get rid of the negatives so they stop canceling out the positives. What can you do to a negative to make it go away? Or what can you do to the number to make the negative go away? What are some ideas? And this is for anybody that wants to pitch in.
Multiply by -1.
All right, I like your idea. We're gonna go ahead and we can multiply by -1. What else could we do?
Use the absolute value.
Oh, nice. We could use absolute value. Anything else?
Square it.
Yeah, square. So 3 wonderful ideas. Absolute value multiplied by -1 and square. What we're actually going to do is we're going to use that third one. We're going to square the numbers. The reason we don't really know much about why, it has to do with something that's going to happen in chapter 7. There's this thing called, it sounds really funny. It's called a chi-squared distribution. And basically, the important part of that is when you square stuff, you get really special properties that happen in a data set. So it's going to be helpful to us in like 2 months. Anyway, so we know that we need to square stuff. We're going to put in an extra column here. And what we're going to do is say we took the preceding column and we're squaring it. So we're going to put in a superscript 2. And I'm going to go ahead, I'm going to drop in the square of each number that I have here. And I'm going to let everybody catch up. So we took -25, we squared that, it gave us 625. We took the -15, we squared that, it gave us 225. And we went all the way down like that. I'm going to give you guys a bit of time to get that information down. And I know it seems like a lot of work, but as we practice it, we'll get faster and faster. Anybody need another minute?
Yes, please.
Okay. All right, how we doing? Everybody got it? Okay, swell. So we got all these numbers, the 625, the 225, 25, all the way down and through. Now, what we need to do is add up all these so we can get an average on it. So I'm going to add these up, and it comes out to be 1,750. I'm just going to take that number and write it a little bit higher on the screen here. And I need to clear some space out of the screen. So I'm going to move a couple items here. This will come right back. Perfect. So we've got 1,750. Now, if we wanted to get the average of those numbers, what would we probably take the 1,750 and divide by? Salah Salami, you're next on my list. I don't think I said your name right. How do I say your last name?
It's Selmi.
Oh, Selmi. Okay. Is that a Arabic name?
Yeah.
Do you speak Arabic?
I am half Ecuadorian and half Palestinian, so yeah, I speak Spanish and Arabic.
Oh, nice. Salam alaikum.
Alaikum salam.
Shukran. I used to live in North Africa, and that's probably the little bit of Arabic that I still remember. Pero si tú quieres, nosotros podemos hablar en español también.
Yeah, that's pretty good.
You're being too kind. Thank you. Okay. So we've got 1,750. If we needed to do the average of that, Salah, what would we probably want to divide by?
By 6.
Okay, 1, 2, 3, 4, 5, 6. He's counting them up, and he's saying we've got 6 numbers. Now, this is the part that's really freaky. We're going to divide by exactly what Salah said, -1. We'll probably find out why we did the -1 on Thursday. Right now, it's going to be overload if we go there. We just have to remember that we take the 6 and we subtract the 1. Now, we're going to stop and summarize things a little bit of what we did. So what I'm going to do, I'm going to break out of this mode, and I'm going to use my pointer here so I can point a few things out.
Professor, will we be subtracting 1 in every question like this, example like this?
That is a fabulous question. The answer is yes, unless you go to statistics 2.
Okay. So we're always going to subtract 1.
Yeah, there's only one case where you won't have to do it, but you're not actually going to end up calculating it. Somebody else is going to calculate it for you in that circumstance.
Okay.
So if you want to like put that as a rule in your mind, you'll be fine.
Okay.
Okay, so let's just summarize everything we did because we've been at this a while. When we started this, the first 2 columns that we worked with, were X and the X bar. So we took our X and our X bar here, and what do we have to do with those? The next person I have is Ms. Adriana, looks like it's Shedge? I don't know how to say the last name. Adriana, how do I say the last name?
It's Ardiana, and the last name is Shay.
Oh, thanks, Ardiana. I was way off.
Okay.
Okay, so Ardiana is saying when we did the first 2 columns, we took X and X bar. What do we do with the X and the X bar?
Subtract.
Right on. So Ardiana is looking at them and she's saying, I did the subtraction. So our formula starts off and it says, we took each X, we subtracted it from, here's our X bar, took both of those and we subtracted them. Now, Ardiana, after we did that and we got all these numbers, what did we find that we had to do with all those numbers? What was the operation that we needed to use to take care of the problem with the negatives?
Do the second exponent.
You are correct. Here's our second power. So over in our formula here, it's saying we're going to take each x and x bar, and we're going to square it up. Now, after we squared them, we have all these squared values right here. Teddy looks like it says Sizer. Teddy, what do we, whoops, I guess I'll just leave it there now. Teddy, what do we have to do to that column? There's your hint, Teddy.
We gotta make it all positive.
Something else.
Add it.
Yeah, the summation. So what's our formula, rather, what's our symbol for summation? It's that funny E symbol. It looks like an E. So we're going to slip that on the outside right there. And it's going to help us remember that we have to add all the numbers we have in this column. Now, the last thing we did was we took our total number of observations, which was 6. And what's our symbol for total number of observations? Mariah. Mariah Singletary.
I'm not sure.
What's our symbol for total number of observations, everyone?
Capital N.
N.
Yeah, okay, it's lowercase n. You're not really going to, you're going to use the capital N once more, but just for one thing, and then you'll never see it ever again. We're going to use that lowercase n, and we had to do what with it? We had to subtract 1. So when we do out the math there, we end up with something called the variance, s squared. And the variance, or s squared, is going to equal 350. So what the variance is doing is, well, we'll explain what variance is doing in just a second. I need to emphasize this s squared. Make sure you write that down, because s squared is going to show up in every single formula. You're probably wondering why they didn't just call it v or something like that. And I guess the statisticians thought that would make too much sense. Everybody will know what to do if we call it v. So we'll call it s squared instead. Everybody okay so far? Any questions on anything before we work with that number 350?
Professor, real quick, is the variance always a lowercase s squared?
Yeah, that's a really good question. It's always going to be lowercase s squared. Any other questions? Okay. So the variance is equal to 350. Let's just talk about what in the world variance of 350 actually means, because we calculated it out, but what is that telling us? But remember when we started, the variance, we were using it because we needed to know the average distance between each value and the mean. And we ended up with the average squared distance between each value and the mean. So that 350 was the average squared distance between each number and the mean. The problem is we don't want to talk about square distances because people don't understand them that well. Like if you're speaking to somebody and you drove 10 miles to get to work, they ask you how far you drove, would you tell the person I drove 100 square miles to get to work?
No.
That sounds kind of weird. Like if you're making $10 an hour at a job and somebody says, oh, what's your salary at your present employer? Would you tell them I make 100 square dollars an hour? Or would they look at you really weird?
Really weird.
Yeah, they're gonna look at you really weird. So the same thing here. We don't want to talk about average square distances. We just want to, keep it simple, average distance. So we have to do something that's going to knock out that square. What do we know in math? I guess I kind of went a little too far with the slide. The answer is right up there. What undoes a square in math?
Square root.
Right, square root. So what we're going to do is we're going to roll out the square root, and then that's going to bring us to the standard deviation. So what it's going to do, and I have to move the chat window again so I could see what's down here. I need to see everything you guys see. Perfect. Okay. So what the standard deviation is going to do, standard deviation has a special symbol. We're going to call it S. And we call it S because it's basically the square root of S squared. So the only thing that you have to remember to do for the standard deviation is you got to take the square root of the variance. It's basically the same formula that we just did, only it's under a square root sign now. Everybody okay so far? Okay, so let's actually do out the math and let's find out, what that number really means to us. What do we get when we punch through the square, we do the 350 and we take the square root of that? What's it come out to be?
18.708.
Okay.
Then, yeah.
All
There's
right.
a bunch of other numbers.
Yeah, and a bunch of other numbers, right. So if you're calculating this out and you're doing this by hand and you get like 17.8, 16.8, 21.2, you probably did it fine. You're going to get within probably 4% of this number, and that there's nothing wrong with that. In statistics, you're usually not going to get exactly the same answer they had in the book, but you're going to get really close to it, and that'll be good enough for us. Reason why, everybody's going to round in different places when they're doing their calculations. So if you're studying with somebody, you're not always going to match the same answer they had, but you might be off by a matter of a decimal point or two. Okay, so the 18.7, that's what our standard deviation S is going to be. Make sure you record that symbol, standard deviation equal S. Now, what does it mean? Let's talk about the practical implication, and then we'll be almost done for today. So the standard deviation is something that would help you a lot. If you're, for example, let's say you're looking at a can of paint. You got the wrapper, and here's the wrapper up there on the screen. What kind of stuff do they write down on the label of a paint can? What kind of things do they tell you if you pick one up and start to read it?
Chemicals?
Yeah, to tell you what chemicals are in it, and what else do they say?
Directions?
Sure, yeah, directions. What other things?
How much is it in it? How much is in it?
You betcha.
How much is in it?
Yeah, is it a gallon? Is it 2 gallons? What else?
How long it's going to dry?
How long it'll dry. Oh, very nice. I like that. We're going to use that. So it tells you how long it'll take to dry, and it might say that it's going to dry in 35 hours. And I'm going to drop down to Aaron. Aaron, I think I would pronounce this Sprague. But Aaron, if it says that the paint's going to dry in an average of 35 hours, would you expect that if you used it, paint a room and the room is dry in exactly 35 hours on the nose?
No, I would expect it to dry around 35 hours plus or minus 18.7.
Okay, you knew where this was going, didn't you? Brilliant. That's exactly right. So when we see the 35 hours, 35 doesn't mean that your paint is going to dry in exactly 35 hours. It means it's an average. So Aaron, fair to say there would be some give or take around that average, right?
Yes.
Okay. Now we would probably want to know how much give or take there's going to be. And like Aaron just called out, the standard deviation is telling you exactly how much fluctuation there is. So 18.7 means, like she just said, you're going to dry within 18.7 hours of that average. Everybody okay so far? Questions on anything?
Wait, can you repeat what you just said?
Absolutely. Remember when we see the paint and we're reading all the stuff on the label, like, don't drink the paint for breakfast. And I see people are laughing at me, but people actually try it. They say all kinds of chemicals, don't dump this down your toilet if you didn't use it all or something like that. And they'll tell you the dry time. It'll say it dries in an average of 35 hours. But we know that if we use the paint, it's not going to dry in exactly 35 hours because 35, after all, is an average. There's some give or take to it. And we would like to know, well, how much give or take is there? And the standard deviation is telling us your paint will dry within 18.7 hours of that average.
Okay.
Does that help?
Yes.
All right, awesome. So now I got a kind of challenge question for you all. I'm going to go to Anne-Marie Tarleton with a T. So Anne-Marie, if you were in charge of quality control at a company, like you are this, it says BHR Premium Plus, doesn't tell you who made it, but that paint company, you're doing quality control. Would you want your standard deviation on the dry times really high or really low? Which do you think would be best?
Lower.
Okay, how do you know?
Well, because I think it gives someone more of an indication of what the dry time will be. Because if you're saying 35 hours, but 18, it could be 18 more hours or 18 left. It's going to be hard to plan painting your room.
Yeah, basically what'll happen as your standard deviation goes down, will your consumer find that the product is closer to the specifications or further away from the specifications?
It'll be more accurate, so closer.
Exactly, you got it in one shot. That has a lot to do with quality control, and there's many companies that spend hundreds of millions of dollars a year making sure that if they say a light bulb lasts for 20 hours, it's not going to be like 21 hours or 18, it'll be like exactly 20 hours to the second. And they place a lot of attention doing that so that customers feel like they're making a reliable product. Questions on anything yet? Okay, seems like we're doing all right so far. And we talked about it, standard deviation is telling us how much flux there is on the average, how to interpret the 18.7. Okay, I'm gonna hold off on the next slide right now. Let me bring us back to where we just were. And what we're going to do on the next slide starts to tell us a little bit about why all of a sudden we had to do that N-1 thing, but it gets kind of elaborate. So we'll hold off on that. We won't do that until the, what day is today? Today is Tuesday. We won't do that until Thursday's class because I don't want you guys to feel like you're on overload any more than we need to be. And what we'll do is we'll stop here. I'll be here for a while in case you guys have any questions. In the textbook, you have a PDF. I'm going to make sure the homework X's are circled. Those are going to be in section 3-2. And what I'm going to do is I'm going to take a minute to bring that PDF up on my screen. I'm going to break out of this mode. And you're not going to see my screen for just a minute as I'm going to hop into the Moodle site so I can turn that on. It's going to take just a minute to load the pages I want to show you because I'm running Zoom and it's going to slow the system down. Okay, now it's just almost there. Okay, I'm going to turn this back on and share it. Perfect. Okay, everybody should be able to see my PDF now. Can everybody see what we have on screen that says applying the concepts?
Yes.
Okay, thank you. You're not going to do applying the concepts, but that's what it's showing right now. And exercise set 3-2, what you guys are going to be working on is where it says in exercises 7 through 13, find the range, variance, and standard deviation. And I don't have the circle in there in red, so I'm just going to dialogue you through it instead. For each of those data sets, you do not have to calculate the range. What I want you all to work on is the variance and the standard deviation part. So we'll be doing that for number 7 and number 8, variance and standard deviation for each data set. And in number 7, when they're saying, are the data consistent or do they vary? You don't have to worry about that part of the question. You don't really have enough information to answer what they're asking. So all you're going to worry about for 7 and 8 is just like brute force of the formula, calculating out the numbers, making sure you got the formula down. Now for numbers 9 through 12, those are over here. And actually, we'll just do 9 through 11 to make it a little easier. As I look in number 12, the data values are like 10,000, 40,000. You don't want to square that stuff in your calculator. It's going to be a little overly taxing. Will take away from the learning objective. So for numbers 9, 10, and 11, what you're going to do is, instead of calculating both variance and standard deviation, just calculate the variance for each data set, and then you're going to compare from one data set to the next. Like, for example, number 9 has 2 data sets. You're going to do the variance for the data set up on top, and then the data set for the one on the bottom, and then you're just going to compare and find out which data set is more variable. They're going to get into something in the answer book called coefficient of variation. You don't have to worry about that. Any questions on what's going to happen with the homework? Okay. When we come in on Thursday, it's most likely going to be the case. We'll do a whole bunch of exercises, like practical exercises with standard deviation and variance. We want to make sure we really understand what those are about before we start to proceed. The next set of concepts we're going to come into jump off of the variance and the standard deviation, and we take the variance and we start plugging it into other formulas. But I don't want us to start doing that if we don't really have a good handle on what the calculation of variance is about. So we'll make sure we have a great foundation, and then we'll start to move into things like the Chebyshev theorem, the empirical rule, things that will help us find outliers. So far, anybody have any questions about anything else? And I see.
I do, Ashley.
Hi, Ashley. How can I help?
Hey, I just have a couple questions. So I feel kind of wary about when you say, like, don't worry about so-and-so. No offense or anything. But when you say, like, don't worry about the coefficient of variation, does that mean
I'm not going to ask you on
we're not going to talk about it in the future at all?
Yeah, you're exactly right. I'm not going to talk about it at all. I'm not going to ask you on the test, what's the coefficient of variation?
Okay. Because, like, the chapters are, you know, the last, what is it? What chapter are we on? 3 is like 80 pages.
Yeah, it's a big one.
So sometimes it's hard to know.
Well, what we did that I hope will help out is inside the chapter. Let's see if I can find a good example of this.
And I mean, I think you do a great job of like walking us through the whole thing, but it's just overwhelming when you look at it, because there's like all the learn in Excel and learn and, you know, like all the questions and review. So
I was going to try to do a example of something for you all. Okay, well, this is not going to work. There was something I was going to mention in specific to a book page. So for your particular question, you won't have to calculate it. And the reason why, it's one of those things you're going to see once, and then we're never going to work with again for the rest of the course. So it's not really going to help us moving forward with anything.
okay.
And what I try to do also is in the chapters, if I see that there's anything in there that we're not going to do, I'll cross it off. So you don't, I don't want to say you won't read it by mistake, but so it'll help you prioritize your time.
Yeah, I have noticed that here and there, and that definitely helps. I was also wondering, like, does range have a symbol? And
that's a great
also, like, why would anyone ever use range?
That's a really smart thought. And the answer is we would use it for the frequency distribution. And other than that, there are other places where you will use it sporadically outside of statistics. Once you leave the once you leave the frequency distribution chapter, you'll never see it again.
Okay. And just one more thing, sorry to have so many questions, but when in the reading, they did the variance and standard deviation based on
Samples.
population, like at first anyway.
Yeah, that's a really, really good comment. When you guys do your calculations, this is something that I was going to go more into Thursday because it can get complex really fast. But the good news is for you guys, when you have to do a calculation, you'll only have to do a sample variance and sample standard deviation calculation. I'm never going to ask you to calculate the population variance and the population standard deviation once. And in fact, what I'll do, there's something I can share that'll help expand on that. And let me flip the screen over. Now there's a lot going on this screen. That's why we weren't going to, I usually don't like to go into it until the day after we talk about standard deviation, but the only calculations you'll ever have to do are in the sample columns.
Okay.
The population, we talk about it only because eventually when they give you population standard deviation, population variance, it's going to come pre-calculated, although they're going to give it to you very often with only the symbol, the shorthand symbol. So we have to know what the symbol is so we could recognize it.
Okay, great.
Any other questions?
Thank you.
You're welcome. Anybody else have any other questions? I'm just going to check the chat room, see if we're good there. Okay, I see somebody's, Victoria is saying just to be 110%, the standard deviation is give or take of the average. Victoria, was that a question or was there something about the 110% you were asking about? Oh, okay, I think I get you now. Are you asking if it's trying to tell you how much give or take you will be from the mean when you're any given number in a data set? I'm not sure if Victoria is still here. Okay, I think she might have left, so I'll be here for a few more minutes in case she comes back. Anybody else have any other questions? All right, it's a pleasure to be with you all here, and thank you for dialing in. We'll pick up again on Thursday. We'll do some more stuff with variance and standard deviation, and then eventually we'll get into a little bit more section 3-2. And I'll post the recording in the usual recording file, probably within about 2 hours, as soon as it gets done getting created on the computer here.
Thank you.
You're welcome. Have a great day.
Have a good day.
Thanks,
Yeah.
Professor.
Thank you.
Have a good
Bye.
day, Professor. Thank you, Professor.
I actually have a question.
All right, is that Michael?
Yes. Wait, so what does like the definition of standard deviation, like what is it like?
It's giving you the average distance any number is from the mean of the data set.
Average distance of the what?
Average distance of any number from the data set mean.
Okay. Thank you.
You're welcome.
Have a good one. See you Thursday.
Have a good day, good night, and a happy Wednesday.